In this video, we'll discuss data augmentation, probably the single most important way to regularize modern deep neural networks. The more training data we have, the more our networks become constrained to actually fit the function we want them to fit, rather than fitting another function that would also fit a smaller training data set. So if you can generate additional training data, then this is a great way to regularize our networks. Let's dive right in. Data augmentation. So the simplest way to get better performance in machine learning is to simply get more data. There's this fundamental slogan, there's no data like more data. This is, of course, might sound dumb, but if you can get more data, then get more data. It typically helps a lot. Here we have a visualization of some curve fitting based on relatively few data points. If you just get more and more data points, you will get a better and better fit. And if you have the choice between investing a lot of time to build a better model or actually go and get more data, and both of that is roughly the same cost, then getting more data will probably give you better performance. You can also, of course, go and get data from related problems or related sources, or you can generate this data yourself by data augmentation. And data augmentation is actually really probably the most important regularization method in deep learning. So what is data augmentation? It's very common in deep learning, and it's used to create additional training data from your existing data. We can very nicely give examples here from computer vision because we can visualize them, but we'll also see data augmentation for other types of data later on. So if we have an image of a cat, like this one, and if we make it smaller, well, the human visual system would still say, well, that's still a cat. If we reflect it, then we would still say this is a cat. If we would rotate it, we would say it's a cat. If we stretch it, then, well, it's probably still a cat. Maybe that's stretching it a little bit. But if we flip it completely around, then at some point it's looking less and less like a cat. But you're already seeing where I'm going with this. We can do all of these different transformations of the data and still preserve the class cat, unless we do too much of these transformations. At some point, it's actually not a helpful data augmentation anymore. So there are things you can do that would be hurtful to have in your training data. Most importantly, the hypothesis that we learn, so the model that we fit, will actually learn a representation that's invariant to these perturbations. So if for all of our training images, we rotate them, say, up to 30 degrees or something like that, then, and if we then take a test image and we rotate it a little bit, then typically we'll get a similar prediction as for the non-rotated picture. And that means our model is now relatively invariant to these perturbations. And while this data augmentation often yields very substantial improvements, however, of course, you need to know which perturbations you want to be invariant to. If you have a task such as SVHN, which is actually looking at numbers or just MNIST, and then you reflect your data, then, well, all of a sudden, a 6 might look like a 9. And that's not what you want. So you need to be careful about what type of transformations of your data you want to allow. So one question would be, well, what data do we actually apply these augmentations to? And I'll actually give you maybe half a minute to think about this, and then we'll move on. So the solution is we only apply this to the training data. We definitely don't only want to apply this to the validation data or only to the test data because, well, whatever we do to the validation data, we should also do to the test data and vice versa in order to have the validation performance be an unbiased estimate of the test performance. We could, in principle, also apply it to all the data. How would we do that? Well, there we would, during training, we would do transformations, and at validation and test time, we would also do transformations. So given a test image, we would do different types of transformations of it, and then, for example, average the results. And this is actually also possible. It's called test time augmentations. The typical type of data augmentation that is used most widely is only for the training data. All right, so basically there were two correct answers here. Only the training data or all the data. So we just looked at computer vision for some, well, in particular object recognition, what some of the transformations we could use there. For other domains, we can also have them. For example, in speech recognition, we could simply add some background noise, or we could change the tone a little bit, or we could change the speed of the speech. And still, we should be able to recognize the same utterances, the same words, etc. And therefore, we would want to have representations learned that are invariant to these transformations. And if we create data augmentations that include these, then we'll encourage a learned representation that is indeed invariant to these. For example, if we do text classification or NLP in general, then we could also think about replacing words by synonyms, etc., etc. So for most applications, when you think for a little bit, you can come up with some data augmentations that you would actually kind of like to be invariant to. Now, one question that we already touched on before, how much of these augmentations do you apply? Well, if you change the speed of speech by a factor of 5 or so, then at some point you probably don't want to be invariant to this anymore. It doesn't sound like the same utterance anymore. If you stretch your cat tenfold in width or height, then it also doesn't look like a cat anymore, etc. And so the question is, well, how much of these augmentations do you apply? And that can actually be cast as a hyperparameter optimization problem. So you simply say, these are my possible augmentations. Now please go find me the hyperparameters that actually, when you train with them, give me the best validation performance. And that's precisely what the work on AutoAugment by Kubuk et al. Did. So they realized that, well, we can easily evaluate a combination of different augmentations. So not only just one, but a whole combination of different augmentations. And of augmentations and their respective strengths. So how much of each of them do you apply? And in order to do that, you would simply train the model with this combination of augmentations and then evaluate the resulting model on a validation set. And then you get a scalar score of how good is this combination of augmentations. And then you can actually have a meta-level search process that searches for good settings of these hyperparameters automatically. And you can use many different methods for that. We will cover these methods in our module on hyperparameter optimization. But in AutoAugment, Kubuk et al. Used a simple policy gradient method. Now, the results of that were that, well, performance was much, much improved over previous pipelines where there was just some manual augmentation. But this was a paper that had a very large computational cost in order to search for the best combination of these augmentations. They evaluated about 15,000 different combinations of different augmentations for each data set. Then a follow-up work in the year after by the same first author actually dramatically simplified this process. So rather than optimizing the choice of the augmentations, they now actually sampled random augmentations. And there were only two hyperparameters that remained to be tuned, namely capital N, how many transformations to use at each time. So they would still use more than one transformation at a time. So for example, they would shrink the image a little bit and rotate a little bit. So how many of these transformations to use at each time? And then capital M, the strength of all of the different transformations. And this was just one hyperparameter that was the same for all the different transformations. And this actually was dramatically cheaper than auto-augment and just yielded the same or very similar performance. And so rand-augment actually then became a pretty common thing in the computer vision literature because it yielded good performance and was fast. In a recent paper by my PhD student Samuel Müller and me, we actually introduced a yet simpler method that is yet better. So this is called TrivialAugment, and this works as follows. So it's really simple. For each image, you sample just a single augmentation, and then you sample a single strength for it. And that's it. And there is no need for tuning, other than, of course, choosing the candidate set of augmentations and strengths, but there we took exactly the same that auto-augment and rand-augment also used. And so while for auto-augment, you had to evaluate these 15,000 different configurations, for rand-augment, you still had to tune 2 hyperparameters, so that might still be 50 evaluations or so. For TrivialAugment, there's 0 overhead. And the performance is actually even better than rand-augment and auto-augment. And so we believe that this is going to become a new baseline or a new default for many different computer vision pipelines. Of course, I just mentioned there's no need for tuning at all. However, of course, this choice of the candidate augmentations and of the strengths, the range of the strengths, that is still actually an interesting hyperparameter. You could also say, well, I want to have this set of different augmentations, but I want to have a much higher likelihood for this particular augmentation and a lower likelihood for these other augmentations. So you could actually still do hyperparameter optimization in this space, and probably one can actually improve this further. But it is already a very well-performing baseline, very surprisingly so, given that a lot of compute was spent on this problem before. All right, so in a generalization of this data augmentation is that really what we want to achieve in our models, we want to be robust to noise that is being added in some way. So for example, by this random transformations, or also just to random noise that is added. So, and this noise can be added in various places. So it can be added at the inputs, and then we get exactly data augmentation. It can also be added in the hidden units. So that would be data augmentations at various levels of abstraction. And you could even also use the same transformations as were used in TrivialAugment, etc. And I don't actually think that has been done, but that would be interesting. You can add noise, and this is then typically Gaussian noise, to the weights of your neural network. And that is actually a stochastic implementation of Bayesian inference. And Bayesian inference we haven't covered yet, but we will cover it in our module on uncertainty in deep learning. And so basically, if we add some random noise to our weights, then we become less sure in our predictions, or we can converge less to a region of the space where a very small perturbation of our weights would already change our predictions much. Those so-called sharp local minima are actually quite prevalent in deep learning, and these sharp local minima lead to poor generalization because sometimes, well, actually the test distribution is slightly different than the training distribution, and then in these sharp local minima, we don't actually generalize very well. But if we add some noise to the weights, then actually the optimization is driven more towards parts of the space where this addition of noise is not so bad, so more robust regions of the space that where also slightly different inputs will be treated quite similarly. And so that's why this is also a nice regularization technique. And finally, the last place where we can add noise is in our output targets. So there, what we would do is for each of our outputs, we would not say, well, this here is, say, a cat with probability 1, and this here is a cat, this here is a dog with probability 1, but we would rather say, well, this here is a cat, and yeah, give it a 0.99, for example. And then when we optimize cross entropy, then actually cross entropy does not try to go as close to 1 as possible, but more as close as possible to 0.99, and it will then also be less overconfident in other parts of the space, and that gives us nice regularization effects. So previously we talked about adding noise to our inputs, but it was always random noise. It was random transformations or just random pixel noise. And you can also add non-random noise, namely noise that is adversarial, noise that makes the input image look like a different class to your neural network. So this is the area of adversarial images, also related to adversarial attacks on neural networks. And these go as follows. So basically you take some image, as of this panda, for example, and then you compute gradients with respect to the inputs. So you backprop all the way through to your network, to the first layer and one further, namely to your inputs. And for each of the input pixels, you actually go in the direction that makes the classifier as bad as possible for this input image. And so that would be the gradient vector. And if we go along the line of this gradient vector just a very little bit, we end up at an input image that to us as humans looks entirely indistinguishable from the initial image. But to the network, this is actually now a given with a probability of 99.3%. And that is, of course, ludicrous. And this does, well, give rise to this area of adversarial attacks, which is very problematic for neural networks, and also, of course, actually for other models like logistic regression and so on, where we can compute gradients. But here, one way we're actually exploiting this for doing better training and for regularization is to actually, well, train a network on original examples and then generate adversarial examples. And then we simply add these adversarial examples to the network. So we would add this image and say, no, this is not a gibbon, it's a panda. And we'd retrain and then do a loop here over this process, train a network, generate more adversarial examples for this network, add them to the training data, and keep going. And what this does is it encourages local constancy. So local constancy means if you go in any direction not too far from your current image, then you should typically not change your class. And by doing so, this mitigates the sensitivity to small input changes. The downside of adversarial training, of course, is that it is more complex than standard data augmentation because it requires this iteration between standard training and generating adversarial examples. But nevertheless, it's a nice technique that does improve generalization typically. All right, this brings us to the end of this video. And as always, I'd like to leave you with some questions. I encourage you to have a look at them, and I'll see you in the next video.